Good morning, one and all. Welcome to another session on computer organization. This is Dr. Dinah here. We have been looking into the design of a hardwired control unit. And we started with a circuit diagram, coming up with a primitive structure, including some decoders and some control logic gates. So this circuit that we see here is the one in which we take input from the instruction register and give it into a set of decoders and to generate some control inputs. In a hardwired control unit, these control outputs are generated using the hardware circuit. So we are not going to have any operating system or program that controls everything. We are going to have a hardware that is going to control other parts of the hardware of the computer. So that is called as a hardwired control unit. This hardwired control unit receives its input. What are the inputs based on which I have to generate my output? My input includes the instruction which I give. The user's instruction has to be taken as one input. And we also have a clock input that can be given as the timing signal. So based on the clock, I have to take the clock from an external clock generator. I have to analyze the bits given in the instruction. Based on that, I have to do something and generate some control output. That's how the circuit is designed. So we started with the basic design and said we have a decoder which is a 3x8 decoder. This decoder derives its input from the opcode bits, bit 14 to 12 of the instruction register. So the user's instruction which has to be executed is present at the instruction register. That is given as input to the decoder, and the decoder generates signals D0 to D7 from the 3 bits of the opcode. So that's the first step. And we have seen that the bit I5 or the MSB is used for indicating whether it is a direct or an indirect address. So when we look into the instruction format here, we can see that for a memory reference, there are 3 types of instructions. One is a memory reference instruction, a register reference instruction, and an IO instruction. For memory reference instruction only, the bit 15 is used. It is set to, it is called as I, and for bits 14 to 12 are referred to as the opcode, followed by 0 to 11 bits, which are 12 bits, are used for indicating an address value. So memory reference instructions are instructions that go to the memory, fetch some data or take some data from the accumulator and store it back inside the memory. This is the basic idea behind it. So whichever location I want to try and access in memory, whether it is for a read operation or a write operation, the address from 0 to 11 bits can be used for reference. And what should I do with that is mentioned as the opcode from bits 12 to 14. And I indicates the direct or indirect memory address access. We will see what difference it makes with bit I here. We already had a run through of earlier register reference instructions. So register reference instructions have bit 15 set to 0 and the opcode bits 14 to 12 are set to 1, and the rest of the 12 bits 0 to 11 indicate what operation have to be performed using the instruction. Some register transfer instruction can be given using those 12 bits. And we have seen 12 different instructions under the register reference category. And if the bits are 12 to 15 are set to 1, then it indicates that it is an IO operation. For IO operation also, we have bits 0 to 11 used for indicating the operation to be performed. So this is the set of computer instructions which we are trying to perform using the basic computer. Now for this computer, this is the design that we have come up with. So this, based on the instruction format, I am using that instruction format I'm drawing the bit values from the instruction register, and according to that I'm trying to generate some signals. So here I have taken bit 15 into a flip-flop I, and the register content from 14 to 12 bits are given into a decoder. Now a decoder's function we have seen, it takes a 3 or n bit input and it generates 2 power n outputs. So based on the 3 bits of opcode, one of the outputs will be enabled. So from if I give bits 12 to 14 to the decoder, it generates output D0 to D7, and only one of that output will be active at any point of time. The rest of the outputs, if D0 is active, D1 to D7 will be 0. That's the functioning of the decoder. With this in mind, we started understanding certain other aspects. So we saw any instruction for execution, the first 3 timing cycles are going to be the same. These timing cycles are generated by the external clock that is given, and in the circuit you can see that it is called as a sequence counter. The sequence counter takes the external clock and it generates timing signals T0 to T15. Suppose if my instruction gets completed by the end of time cycle T4, then the sequence counter is again cleared. So I clear the sequence counter and set it to 0 so that it can again generate from time cycle T0. So for any instruction in the basic computer, it does not take more than 16 timing cycles. So T15 is the highest number. So to reach T15, T0 to T15, we need 16 outputs. So we have used a 4x16 decoder, and this decoder receives its input from the sequence counter. So a sequence counter gives 4 inputs, 4 bits to the decoder. These generate T0 to T15 timing signals. This is what we have seen till the previous session. Now in time cycle T0, we can understand that all of the instructions have the same mechanism, same way of working for time cycle T0, T1 and T2. Why is that so? Because for every instruction, I need to first read the instruction from memory, bring it to the instruction register, and I should make sure that the program counter is there to look into the next instruction. And then I should give all of those instruction register and give it to this decoder circuit. Only after I get an output from the decoder circuit, I can identify what type of instruction it is. So until that point of time, whatever instruction is given in memory, it is going to perform the same tasks. So until T3, we need not worry about what type of instruction it is. We are going to check on any one methodology only. So here if you look at this, now at time cycle T0, we understand that the program counter is used for storing the first instruction, the address of the first instruction. So that address is brought inside the address register, because every time we try to access memory, it is always through the address register. Whatever address is there in the address register, only that the memory unit will look up. So any address you want, anything that you want to do with memory, you should first bring the address into the address register, and whatever data you take or write into memory has to be placed inside the data register. So these two registers are going to be used for accessing the memory. One is for address, the other is for data. So based on that idea, we are taking the content of the program counter, which has the first address of the first instruction, and we place it inside the address register. Once that is placed, I am going to start executing that instruction. So I need to make the program counter point to the next instruction. So at time cycle T1, I increment the value of PC, and I parallelly read the memory content of address AR and put it inside the instruction register, which means I have read the first instruction into the instruction register. This is completed at time cycle T1. Then we move on into time cycle T2. At time cycle T2, the instruction register is read by all the decoder circuit. So it decodes that bits of instruction register, bit 14 to 12, it is decoded, and bits 0 to 11 which are there in the instruction is now placed inside the address register, because for any memory reference or for memory reference instruction, that is the address. So it's usually the address that is placed in the bits 0 to 11. So that is sent to the address register, and the bit 15 of the instruction register is sent to the flip-flop I. So this is done in common for all types of instructions. Then once I have decoded, I have to identify what kind of instruction we are dealing with. So to understand that first difference, we will see. Now, the major difference between memory reference and other types of instruction is that if bits 12 to 14 are set to 1, then it can either be a register reference instruction or an IO instruction. So for any other combination only, it can be a memory reference instruction. So this 3 bits are sent to the decoder, and the decoder's output are D0 to D7. So D7 can be 1 only if all 3 bits of that decoder input are set to 1. Only if all bits 12 to 14 are 1, then my output of the decoder in this circuit will be 1. So if bits 14, 13 and 12 are all set to 1, then my output will be D7. D7 alone will be set to high. D0 to D6 will be set to 0. So that's one difference. So using that difference, I first identify whether it is a memory reference instruction or the other 2 types of instruction. So it can either be a register reference or a IO instruction. So I first look into signal D7. If D7 is 0, I identify that it is a memory reference instruction. If D7 is 1, it can either be a register reference instruction or an IO instruction. And yeah. It can be an IO instruction. Done. Now what do we do? The next thing is, once I have identified this, I should then look into and find out what exactly is the type of instruction. Whether it is a register reference instruction or an IO instruction, or is it a direct memory access instruction or an indirect memory access instruction. So where do I find that difference? That difference I can find in bit 15. So bit 15 is also called as I. That value is stored in the I flip-flop. So if D7 is 0, it's a memory reference instruction. And if I value is 0, it becomes a direct memory access. And if I value is 1, it becomes indirect memory access. And in the case of D7 being 1 or bits 12 to 14 set to 1, then if bit I is 0, it infers a register reference instruction. And if bit I is 1, it becomes a IO operation or an IO instruction. So the next thing I look into is the bit I. When D7 is 0 and I is 0, it is direct memory access. When D7 is 0, I is 1, it becomes indirect memory access. Both of them are memory reference instructions because D7 is 0. And when D7 is 1 or bits 12 to 14 of the instruction is set to 1, then I check the I value. If I value is 1, it is an IO operation. If I value is 0, it is a register reference operation. So this is done. Once this is done, then I check at time cycle T3, all these are only check operations. So it can run parallel. I have not executed anything. So at time cycle T3 itself, I can start with the execution of IO instruction if D7 is 1 and I value is 1. If D7 is 1 and I value is 2 at time cycle T3, I can execute a register reference instruction. And if D7 is 0 and I value is 1, then it is an indirect memory access. We have understood the difference between direct and indirect memory access. I'll deal with it very soon. I'll once again redo it so that it is easier for you to understand. Now, to understand that, let me use the board once. That way you will be able to understand what it means. So when you try to differentiate between direct and indirect memory access, imagine this is the memory unit. In the memory unit, I have a lot of memory locations. Imagine this is my memory location 100. At 100, I have an instruction with direct memory access. Direct memory access means bit I is 0. I have some read operation, then followed by an address. Say assume that address is 125. Now I go and look up at memory location 125. At 125 I have A equal to 30. 30 is the value which is there in the memory location. So 30 is the value that I will read. This is called as direct memory access. In indirect memory access, I have the bit 15 set to 1 followed by the same read instruction. I still have the same 125 here and assume this is 100 only. Okay, same place. So instead of 0, I am having 1 here. That's the only difference. Now at location 125, imagine I have the value 30 only. But when I say indirect memory addressing, then it means at 125 I cannot find the data. I can only find the address of the data at 125. That is called as indirect addressing. So I should go find out this 30 and I then should go to the memory location 30 and find out the value. So 50 becomes the data on which I should operate. So that is the difference between direct and indirect memory access. I think I think that's more like it. Yeah. So you have the direct memory access and the indirect memory access. This is indirect. Okay. Now there are two types of memory access, direct and indirect. And every time I use direct access, my value of I bit will be 0. And every time I want to use indirect memory access, my I bit is going to be 1. With this idea, now check this. So in this we can see that for direct memory access, I am looking into the memory only once. I have an address, I look up, I find the value. In indirect memory access, I have an address, I look up, I find another address, then I look up once again to find the data. When I look into this circuit, at time cycle T3 itself, at time cycle T2 itself, if you see here you can find, at time cycle T2, we have already put the values of the instruction register 0 to 11 in the address register. So this 125 I have already placed in the address register at time cycle T2. So for direct memory access, I need not worry about the reading or finding another address value. So at time cycle T3, if it is direct reference, I am going to do nothing there. Okay, I'm just going to wait. The CPU is not going to process anything at that point of time because that address is already loaded inside the address register. But if it is indirect memory access, I should go and find out at memory location 125 what is the exact address of the data, which is 30. Now this 30 has to be brought into the address register. Okay, so address register means that is address register is like the gate. I need to put whatever I want to access. I have to put it inside the address register. Only then I can read that location. So I need to read 50. To read 50, I have to place its address in the address register. So this 30 has to be placed in the address register. Where is this 30? It is in a location addressed by the memory address. 125 is currently in. When I am executing this instruction, address register's content will be 125. Okay. But I want to access in the next task flow, I have to access this location. So what I do is at address register, I am going to read this particular memory location and this value I am saving into the address register. Is that clear till here? Yeah. And at time cycle T4 only, I start executing my memory reference instruction. So this is indicated using logic. So at D7 dash means it indicates a memory reference instruction. When D7 is dash and I is 1 at time cycle T3, it means it is a indirect memory access. So I have to perform this memory address of memory location addressed by address, that content should be brought inside the address register. And D7-I-T3, I am not going to do anything. When I value is 0, it means that it's a direct access. Okay. Now, at D7-I-T3, D7 means it is either register reference or IO. If I dash means I value is 0, at time cycle T3, it's a register reference instruction. And D7-I-T3 is a IO instruction. We have already looked into so this is the same thing. We have already looked into a set of register reference instructions. In register reference instructions, the value of instruction register from bit 0 to 11 are used to indicate instructions. So, because all opcode bits are set to 1, I can't distinguish between different instructions using bits 12 to 14. They are predefined for register reference instruction. So, for register reference instruction, we see that the bits 12 to 15 are 0, 111 only. So, to identify what exactly is the register reference instruction, I have to use bits 0 to 11. So, when I use bits 0 to 11, I can independently execute 12 different types of instructions. These are the 12 different instructions that can be executed on a register reference mode. The next thing we will see is about memory reference instruction. So, we are going to start talking about memory reference instruction now. So, when does memory reference instruction happen? Tell me. When does a memory reference instruction happen? When the bits D7 is 0, so I'm going to talk about memory reference instruction. Memory reference instruction happens when D7 is 0. So all controls information will start with D7 dash, and then it can either be I or I dash. I indicates direct memory access, I dash indicates indirect memory access. So I am not going to mention the value of I. I can either be I or I dash. Both are applicable for memory reference instruction. So from henceforth I will not mention the value of I. Then you have T. It starts with either T3 or T4. Okay. Now we are going to start listing our operations. First case is an indirect access. Indirect access means D7 dash I value should be 1 and T3 row. What do I perform? What do I perform? I bring the content of memory addressed by the address register into address register. Is that understandable? Because I am doing a double reference of memory for getting the data. So that content is brought into address register. If D7 dash I dash T3 ante means D7, it's a memory reference instruction, and I dash is 1. I dash means I value is 0 at T3. It's a direct memory reference instruction, so I will do nothing here. Is that clear? So we have completed time cycle T3 for memory reference instruction. So we are going to start executing our memory instruction only from time cycle T4. And to identify what type of instruction we are going to use in memory reference category, we are using the bits 14 to 12 of So this is my instruction format. Bits 14 to 12 are going to be used as inputs for indicating what type of instruction I have to execute. So with that in mind, this is given as input to the decoding circuit, and I generate signals D0 to D7. D7 is always dash. So D7 is always going to be 0 for memory reference instruction. So I am going to use signals D0 to D6 to differentiate between different memory reference instructions. So I am going to have 7 different instructions because we have only 7 different values. D0 to D6 are the values that differentiate between memory reference instruction. So for D0 I am going to have an instruction. For D1 I am going to have an instruction. Likewise I am going to have 7 memory reference instructions. So we are going to look into each of these memory reference instructions. Okay. The first instruction that we will look into is when D0 is 1. When D0 is 1, that is the first type of memory reference instruction, and we are going, the instruction is called as AND. The instruction is AND. When I use AND, it means I have to perform an AND operation between 2 elements. The first element by default is the accumulator, and the second element is the content that I read from memory. Because it's a memory reference instruction, one of the operand will be from memory and the other operand, if required, will be in the accumulator. Okay, so I am going to perform an AND operation between a memory location's data and accumulator. So this is the AND operation. So at time cycle when D0 is 1, and at time cycle T4, because T3 is already complete. Whether it is a direct access or an indirect access, I have the address now ready at the address register. So even for indirect addressing, I have brought that address into the address register. So I need not worry about referencing. Now the address of the data is available in the address register, whether it is direct access or indirect access. So I have completed that aspect at time cycle T3 itself. At time cycle T4, I can directly read the data from the address AR. So I have time cycle T4 here. D0 value is 1. All the other inputs are going to be 0. At that point of time, I have to do an AND operation between the memory's content and the accumulator. Now, I should use the accumulator. But a memory read operation, I can't directly operate on data which is in memory. I should first bring it to the some local register, only then I can start working on that data. So every time memory is accessed, the address is placed in the address register, and whatever you have as content to be read from memory, it is first brought inside the data register, and then you do some operation with the data register. If I want to write something into memory, I place the address in the address register, and I place the data which is to be written inside memory either in accumulator or in data register. So this is possible. So every time I read from memory or operate on some data which is in memory, it should either be brought into accumulator or into the data register. Only then I can perform that operation. Now because I have to do an AND operation with the content of accumulator, I cannot bring it into accumulator because it will overwrite the data content of the accumulator. To avoid that, I am not going to work on that. I have to bring the data and put it inside the data register. Okay. Now that it's taking too long, let me start with the instructions in the next session. With this, I am just actually giving this, you take this as an introduction to memory reference instruction. We will look into all the memory reference instructions in the next session. Thank you one and all. Stay home, stay safe. Looking forward to seeing you all very soon. Thank you.